So in this video, we'll discuss the idea that nothing is completely soluble or insoluble. So despite what we said in General Chemistry 1, where we presented this solubility rule table, and we said that, you are soluble if you contain these ions, unless you fall into one of these exception groups here, and you're generally insoluble if you have these, with the exceptions over here. So for example, if we said something like barium sulfate, and does barium sulfate dissolve in water, we would use our solubility rules and look down the list and we'd say, oh, sulfates generally dissolve, but if they're paired with one of these ions and barium's one of those ions, it's going to be insoluble. So if we throw it in water, right, we would expect just to have it sitting on the bottom of the beaker. Now, it turns out that there is no such thing as things being completely insoluble. So actually, let me get rid of that table now. And in this chapter here, we're going to look at solubility equilibria, this idea that these solids can actually dissolve in water. And so you have to recognize these ionic compounds. You have to recognize the polyatomic ions and the monatomic ions and their charges. And we're going to write these solubility equilibria, whereby on the left we start with the ionic solid, and on the right we essentially just break it apart into ions. Kind of like when we had a full ionic equation, we broke the soluble stuff apart into ions. Except here we're saying that there's no such thing as something being completely insoluble. All right, we're going to call this solubility equilibria, and we're going to give it an equilibrium constant of K SP, and the SP stands for solubility product. And so in this reaction here, KSP is equal to the concentration of barium at equilibrium and the concentration of sulfate at equilibrium. And what do I mean by equilibrium here? I mean that I've added enough barium sulfate so no more barium and no more sulfate ions can dissolve. And so what I really mean here is at equilibrium, or a saturated solution. So a saturated solution is one where no more can dissolve. All right, enough blabbing. What is this value? This value is actually 1.07 times 10 to the minus 10 at room temperature. So our knowledge of equilibrium constant tells us that this is pretty small. So you aren't going to get many ions at all. So in General Chemistry 1, right, when we say it's insoluble and it doesn't dissolve, in General Chemistry 2, we can take a more nuanced view and say, well, it doesn't dissolve very much. The product of those ions is only about 10 to the minus 10. Now, we can calculate the molar solubility. So we can calculate the molar solubility, which is the number of moles a compound dissolves in a liter, using an ice chart. And so let me go ahead and set this up as an ice chart problem, and I'll show you how to do that. So in an ice chart problem, what we're going to do is we're going to start with the KSP reaction. So we're going to write basically the ionic compound and the dissolved ions on the right-hand side. And again, just a reminder, right, in Chemistry 1, we said it did not dissolve, but now we're ready to kind of undo the lie. All right, what do we start? Initially, right, we're just going to have solid. We know that solids don't enter into equilibrium constant expressions. Before it's dissolved, there's no barium and no sulfate. We are assuming we're working with pure water. All right, so we're going to calculate what we call the molar solubility. And the molar solubility is the number of moles per liter that dissolves. We're going to give it the symbol S. And although it's a solid, and we shouldn't really be writing this down, we're just going to remind ourselves that if we let S moles per liter dissolve, that concentration will go down by S, and these concentrations would go up by S. And so at equilibrium, the concentration of barium would be S and S. All right, we wrote a KSP. SP is the solubility product. We saw it is 1.07 times 10 to the minus 10, and that's equal to the concentration of barium times sulfate, right? There's no coefficients here, so we don't have to raise it to any powers. And at equilibrium, we've calculated that to be S and another S, so of course that is S squared. So if we want to know the molar solubility, we just need to square root both sides. So we're going to square root 1.07 times 10 to the minus 10. And we can see that's going to be somewhere on the order of 10 to the minus 5. So three significant figures, it's 1.03 times 10 to the minus 5. And it's a solubility, so it would be the number of moles dissolving in a liter. So 1.03 times 10 to the minus 5 moles per liter. Now, in terms of a solubility, when we look at solubility as opposed to molar solubility, so molar solubility is the number of moles per liter that can dissolve. Solubility is the number of grams that can dissolve in a liter. So we can do a little bit of stoichiometry here. Isn't this fun? So we can go ahead and we can say there's 1.03 times 10 to the minus 5 moles of barium sulfate dissolving in a liter of solution, which is primarily water. And if we want to convert moles to grams, right, we just have to add up the weight of a barium, a sulfur, and 4 oxygens, which I get to be 233.4 grams per mole. So now if we multiply those together, we get still a relatively small number, 0.002. I guess I need some more significant figures. 40 grams per liter. If you like, that is 2.40 milligrams per liter. So most of our general chemistry 1 books will say something is insoluble if less than a gram can dissolve in a liter. But we can see here much less than a gram can dissolve in a liter, so only about 2,000th of a gram. So our general chemistry 1 book would say that is insoluble. But now we're a little bit smarter, right? We can say, well, everything can dissolve ever so slightly, and there's about 2.4 milligrams dissolving in a liter. So not much at all, but we can actually calculate it.